right along in Chapter 1. We're moving to Section 1.2 where we're talking about domains and ranges of functions. And so we've already talked about functions having inputs and outputs from the last section. And remember, inputs are referred to as our independent variable. And whereas our outputs are referred to as the dependent variable because it is dependent upon what I put into that function with the input. The collection of each of these values is defined below. So if we talk about everything that is in our input or our independent variable, that is also known as the set of all x values for our domain. And the set of possible output values that I'm looking at for a function or the possible y values are what we refer to as the range of a function. So the domain and the range. Domain is nothing but all the x's. Range is nothing but all the y values. And so what we're looking at here in a table, I'll tell you it's very, very easy in a table. Remember, this is my input and this is my output. And so in order for us to talk domain and range, I'm really looking at domain as my input, range as my output, excuse me. And so then, let me exit out of that. So then whenever I'm asking for what is the domain of a function, I just want, in this case for a table, a list of the inputs, a list of the x values that I have. Well, here are all my inputs. So in order to write the domain, given this table, we are going to write each of those inputs. Likewise with our range, it's the set of outputs or our y values that I have. In this case, it is represented by q. And we look along here and notice that there are numbers that are the same. So instead of writing 8 multiple times, we do not have to do it. It is just a list of values that represent the range. So therefore, I only need to write 8 and 6 once. And so we have 8, 6, 7 as our range for that relation or that function. Okay. Now, before we go into looking at graphs and looking at other functions, we have to make a determination of this notation. Again, we had function notation in the last section. Now we have some notation that represents some inequalities or some ranges of values. So, I'm going to talk that an inequality is a mathematical statement which has multiple solutions. Solutions are nothing but answers, or a range of values which satisfy the statement. Now, the set of all solutions is what we call a solution set. And in set, basically we have, sorry, it keeps doing that. All right, so for our set, that means it's just a collection. This is a solution set for the range of these numbers is 8, 6, and 7, okay? Now, when we start talking about a range of values, we have some inequality symbols. So when I talk about greater than or equal to, you hopefully can recognize this symbol, which means greater than or equal to. If I'm strictly greater than, I take away the line underneath and I have just that symbol. Then I have less than or equal to and less than. So these four things basically in a statement will replace and equals when we're talking about these inequalities, okay, where there's a range of values. Now, for interval notation, I think I left out my R, interval notation, this is some sets of the real numbers can be represented with this, what we call interval notation. Now, suppose that A and B are two real numbers such that B is greater than A. Okay? So, we need to look at a number graph and how do I compare B and A? Well, this next group, I'm going to let B equal 10 and A equal 5. Okay, to where I'm looking at the interval from 5 to 10. Okay? All right, so we're going to look at multiple examples using these numbers. I'm going to start with this one where I have a parenthesis 5, 10 with a bracket. And so basically, in interval notation, this is just a shortcut way in order to solve or look at a range of values. So I'm looking at all the numbers from 5 to 10. Now, this parenthesis means that I'm not including 5. Okay, it's not an equal to at 5. And in order to represent that on a graph, we will represent a number that's not included by an open circle. So parentheses and open circles kind of go together. And if I have this square bracket here at the end, that means I'm including 10, so the possibility could be equal to 10. Therefore, on a graph, I'm going to darken in that circle and end up having a closed circle. And so if I'm looking at all the numbers between 5 and 10, I'm looking at everything in between. So that would be what my graph is. Now, in some instances, we'll see later on in this section, which calls piecewise functions, you will need something called the set builder notation, which includes all those inequalities that we just talked about on the previous page. So I'm going to say that I have all x such that here I am between 5 and 10. So I would say that 5 is less than. Now I'm not going to put equals because I did not include 5. That was open. So 5 is less than x, which is less than or equal to 10. So these two things mean the same thing. One is what we call the interval notation. The other one is what we call the set building notation. Now, what if I end up doing this? And I kind of switch these around and I have a bracket 5, 10 with a parenthesis. Then I basically just kind of switch up that meaning. Now I'm including the 5 and I'm excluding the 10. So we say, do our little brace with our variable x. You can use any letter, such that we have a straight up and down line. And I'm going to go from 5 to 10. So 5 is less than or equal to this time, because I do have this bracket, which is less than x, which is less than 10, and I'm going to do my brace again. Okay, so this includes 5, but does not include 10, and I need all those values in between. So here's 5, here's a 10, and because I'm including 5 on my graph, I need a closed circle. And I'm excluding 10, therefore I need an open circle at 10. And since I'm looking at the range from 5 to 10, that means I need to graph everything in between. So all the numbers between 5 and 10, including 5, excluding 10. Now, if I end up doing just a double parenthesis there, that basically means that I'm not including any of those endpoints. So to write it in set builder notation, we have all x such that 5 is less than x, which is less than 10, with our brace. And so again, we have less thans that go with our parentheses. We have brackets and equalities. And with our parentheses in this case, because I'm excluding 5 and 10, that means I need to have open circles on each one of those. So I would have a 5, a 10, open circle at each, and I'm graphing and looking at everything in between. So that would give me the graph of that. Okay. Now, I'm going to throw in some infinities here because not all the time am I bouncing between two numbers. What if I go to the opposite sides of my number line and I come here and I come here? Keeps going forever and ever and ever. So I'm going to start with 10, infinity, with a bracket on the left and a parenthesis on the right. So, from what we've seen before, this bracket tells me that I'm including 10. So if I'm going to do the number line, I'm going to graph 10 and just put 10 there, anywhere within that. I'm including 10 because I have that bracket, so I need a solid circle at 10. Now, it means I'm going from 10 to infinity. Where is infinity? Infinity is all the way to the right. So as far as I can keep going, the graph of this, we do something that looks like that. So by interval notation, I'm saying 10 to infinity. But if I look at that graph, I could say I'm starting at 10 and I want all the numbers that are bigger than 10 or greater than 10. So I could, in my set builder notation, say, okay, I want all x such that x has to be greater than, and do I put in equals? Yes, I have a bracket and I have a closed dot greater than or equal to 10, closed with a brace, and we have our set building notation. Okay. One last one here that has a definite number on there, and then we will see another example. So what if I end up going from like negative infinity to 5? That's what this interval notation is telling me. Now, notice, and I didn't say this, can you ever reach infinity? Infinity is a very, very, very large number, but you can always add 1 to that previous number. Keep adding 1 and you get a bigger, bigger, bigger number. Therefore, you can never reach infinity, so you can never equal infinity. This is always a parenthesis. This is always a parenthesis. Now, if I were to graph that, that means I'm going up to 5, and I'm not including 5 because I have a parenthesis there. So I'm going to put 5, and because it's not included, I'm going to put an open circle there. And it means I'm coming from negative infinity all the way up to 5. So that means the range of values that I'm looking for in this case are all of these. So from negative infinity to 5, just kind of like you're reading a book, negative infinity to 5. For our set builder notation, we're looking at all x such that I have any number that's less than 5. So I'm looking at everything that's less than 5. Now, I don't have any equals, so I want all x that are less than 5. And that gives me that set builder notation. X is less than 5. Okay? All right, one last one of these. And I'm going to go from negative infinity to positive infinity. Well, where does that look like, or what does that look like on the number line? If I go from negative infinity and I come up on this number line, I keep going, going, going in forever, and I mark that arrow, negative infinity to positive infinity, represents everything. So my graph, I could just fill this in, darken it in if I want. That would be the graph of everything. And in a case for set builder notation, there's really not any inequalities there. We just have kind of this funky little R, which represents all real numbers. Okay? All right, so let's kind of practice this notation a little bit so that we can do some of these sets, and then we get into some graphs. Now, to combine two inequalities together using inequalities or the set builder notation is what we call. We can use the word or to combine them together. Now in interval notation, we use the symbol U to combine two unconnected intervals together, and this symbol, it stands for the union of a set. Just a little extra piece for you there. And so for this exercise, or exercises, these two here, we are looking at writing it in set builder notation and interval notation. So notice I have two different intervals here that I end up having to represent. And so notice by set builder notation, I'm bounded between 1 and 3. So if we kind of go back up here, that's one of these situations where I have my less thans pointing in that direction always. And so the set builder notation for this one, we would want all x such that 1 is less than, now is there an equals? There is a solid dot. So we have 1 is less than or equal to x, and we're including 3, so I want to make sure I have an equals here, 3. So that right there just represents this solution set. Or, we're in set builder, so we combine with an or. Notice I'm looking at all the numbers that are bigger than 5 or greater than 5. So I can say I want all the numbers x that are greater than 5. And that would be my solution set in set builder notation. Now in interval notation, we're going to take on the looks here of each of these, where we're using parentheses and brackets in order to do that. So notice that I have included and included. We need brackets both at 1 and 3. And because I'm bouncing between 1 and 3, it looks kind of like an ordered pair, but not really. So 1 to 3. Since we're in interval notation, we need a U to combine the sets. And Here, we're looking from everything from 5 to infinity. I'm not including 5, so I need a parenthesis. 5 comma infinity. Infinity always gets a parenthesis, and that would be my solution. Okay. Likewise, in the next example, for set builder notation, all x such that. Now notice here, in this solution, what do we have? We have all numbers that are less than -2, and they are actually less than or equal to -2. So I can say x less than or equal to -2, or I'm bounded between -1 and 3. Now I'm including -1, so that means I have to have an equals. My x goes in the middle, all these numbers between -1 and 3, and notice I did not put an equals here underneath that inequality because we don't have a solid dot on 3. Interval notation, what does that look like? Again, read a book. Where are we coming from? We're coming from -infinity with that arrow, and I'm stopping at -2. So -infinity to -2. Now, do I include that? -2? Yes. Therefore, I need a bracket. Union, bounded between -1 and 3, so I'm going to go from -1 to 3. Looks like an ordered pair. I'm going to include -1, exclude +3, and that gives me my interval notation. Okay. All right, so let's use that idea and look at some graphs. We already did some stuff with tables to determine domain and range, so I'm going back to this domain and range. What are our possible x values? What are our possible y values that I have? Now, when you're looking at domains and range, domains, I want you to kind of read it like a book. I want you to go left to right, and you're looking at what x values have y values on them. Okay, so our domain is always in terms of x. When you're looking for range, I want you to go from bottom to top to determine the range on that. So we have a line. If I go from left to right, is there a value on my blue line at x equaling -5? Yes, it's right there. What about at -4? Yes, if I choose -4.5, I have one right there, okay? So if I look along here, there's no open circles, there's no jumps or anything like that. Every number, even if I get over here to like x equaling 10, I'm going to have a y value down here. That arrow represents that it keeps going on and on and on. So the domain for this line, because I have arrows that keep going on and on and on in both directions, that means I can choose any number in order to find a y value that goes with that. Now, likewise, I can look from bottom to top. If I were to kind of go side to side over here somewhere, there's going to be a point on that line if I extend it. If I come up to 7, there's going to be a point on that line if I extend it. So again, in this case, because there are arrows there that are going on in both directions, then we end up having a range of -infinity to +infinity. Now, over here, notice we don't have any arrows. So we have some starts and some stops. So we're going to use some brackets possibly and some parentheses. So again, I'm going to read left to right. There's nothing in blue here whatsoever. So I start with a blue right here at x equaling -1. So there's my function. It starts kind of right here, moving to the right. So I start at -1, and then I end up going where? Well, I keep going. I still see blue until I get to 3, which is down here, okay? So at x equaling 3, I stop. So my domain is going to be from -1 to 3. Now, I do have, let's erase that right there. I do have a closed circle on -1 and an open circle at 3. So therefore, I need to bracket -1, parenthesis, +3, and that is our domain. Now, focus on the y values for your range. So I'm going to go from bottom to top and look side to side and make sure I have a blue value somewhere along this horizontal line for each one of these values. Well, notice we start at -5. So I'm going to start from -5, and I'm going to keep going. I have all this blue over here. Keep going. Now, I want to go to the highest part that I have blue, which is right here at y equaling 4. So I'm going to go from -5 to 4. Now, I'm excluding, -5, so I need parentheses, and I'm including 4. There's not an open circle up here. We don't put points on every single one, so if it's part of the line of that function, then it is included with that. Okay? All right, one more with this graph. What's the domain and range? Domain, go left to right, read a book. I'm starting at -9, and I keep going. Now, this one doesn't have an arrow, but I'm going to tell you that on my open math, they will say if there's not an arrow and not a point at the end, you need to assume that it's an arrow. So we're going to put an arrow on that. So that means I'm starting at -9. But if I have an arrow, that means I can keep going in that pattern. At 10, I'm going to be about here. At 11, we're going to be about here. So it keeps going to infinity on the right side. Now, this is always a parenthesis. Do I include -9 or exclude? Because it is solid, we include with a bracket. Now, if I start from my range, go from bottom to top, notice, again, that arrow, I can keep going down, 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 down to -infinity down here. So -infinity, keep coming through here, and the highest point I have is that guy right there at 4. So we're going to go from -infinity to 4. Again, parenthesis for any infinity. And because I'm including no open circle there, that means I have a bracket there with 4. Okay. So we did a table, we did a couple graphs, now we're going to look at our functions. And there's 3 main functions that we're going to be assessing when we're asked to find the domain of a function. And so we're going to look at polynomials, we're going to look at rational functions, which are fractions, and we're going to look at square root functions, which we saw in section 1.1 what that square root function looked like. Now, polynomials will always have a domain of all real numbers. Or we can do that funky little r. Now, what is a polynomial? Polynomial is something that may look like this. F of x equals x squared minus 3x plus 2. Or f of x equals -3x minus 5. Or f of x equals 7, where it's just a constant function. So there's nothing fancy about it. You could have some squares and powers, but you have a bunch of numbers and variables that are added and subtracted together. The thing about it is no matter how pretty or nasty your number is, anytime you take that number and square it, you'll get a number. -3 times that same number and add 2. Doesn't have to come out to a nice whole number. It could come out to a nasty decimal and it still work. Same way here. I can multiply by -3 any number and subtract 5 and get a number out. Here, it's always 7, so it's always going to kick out a number. And so there's no issues with those whatsoever, making our domain all real numbers, or that -infinity to +infinity. Now, with fractions, rational functions are those functions that are in the form of a fraction. With a rational function, one is looking to exclude numbers for which the denominator blank. Well, in section 1.1, we talked about on that reciprocal function where it is an undefined value that within a fraction that you have 0 in the denominator. So in a rational function, we're okay with putting any number into that function except for what makes the denominator equal to 0. So in a sense, basically you can figure out what makes the bottom equal to 0 and exclude that out of our domain. So in a case where I have something that looks like f of x equals 1 over x plus 2, I'm going to ask myself, what number can I put in the bottom that I add 2 gives me 0? Well, you might be thinking, if you need to, go ahead and set that equal to 0 and solve. So here you could subtract 2 from both sides and get x equals -2. So we need to exclude all values that are -2, or the only value which is -2. So our set or our domain says we want all x such that x is not equal to -2, and that would be a way to represent our domain. Now, if I look at a function, say, where I have x plus 3 all over, say, 2x minus 5, now it is not as obvious as to what makes that denominator equal to 0. So again, here's your trick. Set 2x minus 5 equal to 0, and actually, we could go one step further and make this a not equal. I need that 2x minus 5 to not equal 0. Okay, so I can now solve this equation as 2x by adding 5. I get 2x is not equal to 5. And then dividing by 2 each time, then we get x cannot equal 5 halves. And that would be your domain. So, any number is perfectly fine except for 5 halves. You can't do that. So we have to exclude that. So we want all x such that x is not equal to 5 halves. And that would be our answer for the domain. Okay. All right, and our last function that we're going to look at for domain and at this point is going to be the square root function. Now, we talked about again in section 1.1 where if I had the square root of a -1, we couldn't do it. No number times itself is ever going to give me -1 in the real numbers. So, we have to remember that we can't have negatives under there. Negative numbers don't work with square roots, okay? So when taking a square root, one cannot take the square root of a negative number. Therefore, to find the domain of these functions, we must set what's underneath our square root button, our square root symbol, greater than or equal to 0. So, for example, if I have f of x equals x plus 3 underneath the square root, I need to make sure or ensure that that x plus 3 is greater than or equal to 0. And all we're going to do is take that expression, set it greater than or equal to 0, and solve. Solve means I need to find x. So I need to subtract 3 from both sides. It's just like an equals. What we do to one side, we must do to the other. And we get x to be greater than or equal to -3, which is going to be my function, or my domain, Now, if x is greater than or equal to -3, by interval notation, I could do -3 to infinity as one way to do that. Okay? So, easy as that. Just set it greater than or equal to 0 and solve. Now, that was just a one-step equation. You might end up following through and having a two-step equation or such. Now, the last of our two domains, we're going to mix those three things together. Actually, just the bottom two. What happens if I have a square root and a fraction together? Well, it makes a difference if it's in the denominator or in the numerator. So, remember, for a square root function, that x minus 3 had to be greater than or equal to 0. That's if I just had that square root function. But with a fraction, recall that you could not let the bottom equal 0. So for the radical, to take care of that, I have this. But for the fraction, I can't let that x minus 3 equal 0. Therefore, I have to make an adjustment to my inequality by taking away that equal symbol. So if a radical is in the denominator of a fraction, then we are just setting what's underneath there greater than 0. So when I add 3 to both sides, I get x is greater than 3. So that means if I look at the graph of that where I have 3 and then I have an open circle at 3, I would want everything bigger than that. And so by interval notation, we would be 3 to infinity, and that gives me my domain. Okay? Now, what if the radical is in the top? Radical is in the top. We have to take care of that, okay? So for our radical, for the top, we have to ensure that x plus 7 has to be greater than or equal to 0. Has to be positive. So in order to solve that, that means x is greater than or equal to -7. And if I were to graph that, I would end up throwing -7 down there, and I would have to make sure that I'm greater than or equal to that. So I want all the numbers that are bigger than or equal to -7. But I have a problem on the denominator because, so in the bottom, we have to ensure that x minus 7 is not equal to 0. So, where is x minus 7 equal to 0? Well, what number minus 7 gives me 0? Add that over is one way. X cannot equal 7. So in my graph up here, I'm at negative 7, and I'm getting everything bigger until I get to 7. I can't equal 7, so in a sense, I need an open circle there at that piece. So what would be interval notation for this domain? I'm starting at negative 7. I'm going up to positive 7, but not including it, okay? So I have to do my interval from negative 7 to 7, not including 7, but then I need to pick up everything past 7. So we're not including 7, so I need a parentheses 7, comma, infinity, and that gives me my interval for my domain. So basically in terms, we would say everything bigger than negative 7 except 7. Mathematically writing it down, this is how we would do that. Okay? All right, very good. One last information piece out of section 1, 2, and that is dealing with piecewise functions. And so, piecewise functions are multiple functions which are pieced together. Okay? Let's first evaluate some. We want to be cautious of the interval of your x value, okay? So this is what looks like a piecewise function over here. Okay, I've got multiple functions. I've got my x cubed plus 1, I've got 4, and I've got 3x plus 1. Those are the real rules for these x values. So you're not evaluating 3 functions at the same time, all the time. You only have to evaluate one function, and that one function corresponds to where this x value is that we're being asked of. Now, over here on these intervals, which interval includes 4? Well, is 4 less than 0? No. Is 4 between 0 and 3? No. But 4 is bigger than 3, so I'm within this inequality, and that corresponds to the function that I need to evaluate. Excuse me. So I'm going to take 4, and wherever I see an x in my function, I'm going to put 4. We did this earlier with only one function. So I need to do 3 times 4 plus 1. By order of operations, we're going to multiply first and then add. So 3 times 4 is 12 plus 1 gives me a final answer of 13. If I move across here to 2, okay, f of 2, is it less than 0, between 0 and 3, or greater than 3? Well, 2 has to be between 0 and 3. Therefore, I need to evaluate this function. Well, notice that is what we referred to as a constant function out of section 1.1. Therefore, no matter what x value I have, my y value or my output will always equal 1. Let's go down here to b. Where is negative 3? Negative 3, is that less than 0? Absolutely. So that means I need to use this function piece in order to evaluate f of negative 3. And that rule tells me to take my x value and cube it and then add 1. X value and cube it, then add 1. So therefore, negative 3 times negative 3 times negative 3 is negative 27. That then I want to add 1 to that, which actually gives me then a negative 26. Okay. And finally, we have f of 0. Now notice I've got 0 in 2 spots, and that's where we have to be meticulous of our signs. Notice this is strictly less than 0, and this is less than or equal to 0. So if I'm looking for f of 0, it has to be in this interval. So then I plug it into this function. No x value to plug in there. Always the output of that function would equal 4. Okay? All right. Let's write a piecewise function. Writing a piecewise function, you have to worry about the multiple pieces that you have, and also you have to make sure you watch and look at the intervals at which you are working with here. So I'm going to have f of x equals, and I'm going to do my squiggle. And notice that with this piecewise function, I've got 1, 2, 3 pieces there, okay? So I need to represent 1, 2, 3 functions. And because they are constant, those are those ones that are just a number. So I look across here and I know that that y value is a 2. So that has to be one of my functions. Coming through here, that y value is a negative 2. And coming through here, that y value is a negative 4, always for each one of those. Now, we have to say when those occur. So if, what is the ranges for our x's? Now, each one of these are bounded. So like this one, I'm starting at negative 6, and I'm going to negative 1. So that would be if negative 6 is less than or equal to, because I have a solid dot, x, which is less than or equal to negative 1. So that's, again, that set builder notation where we are in between negative 6 and 1. For negative 2, which is this piece right here, we start at negative 1 and we go to positive 2 on the x-axis. So x's have to be between negative 1 and 2 for my y value to be negative 2. Negative 1. Notice we have a open circle, so it'd be strictly less than x, which is less than or equal to 2. And our last one is bouncing between 2 and 4 at negative 4. So this would be if 2 is open circle less than x, which is less than or equal to, because I have a closed circle, 4, and oops, and that would be my notation there, okay? That's my function. Now, looking at the right-hand side, hopefully you kind of recall from section 1, we had a V-shaped graph, and that V-shaped graph is referred to that absolute value function. So when I'm writing that piecewise function, I need to account for my absolute value, and I need to account for this constant function. So this time, we're going to have 2 pieces here, okay? We're going to have one to be the absolute value of x, and one to be this constant at y equaling 3. So I need absolute value of x and 3. And then, what are my ranges? Well, here we're going from like negative infinity, and this is all of my absolute value, but I'm chopping it off here at x equaling 2. So if I'm less than 2, I end up on the v, or the absolute value. So I want less than or equal to 2. X is less than or equal to 2. And then for my positive 3, I'm going to start at 2 and go to infinity. So it has to be greater than, whoops, I wrote 3. I meant a 2. Sorry. X has to be greater than 2 for the other piece. And that is your function for that piecewise function in particular. All right, and finally, the last little exercise in section 1-2 is for us to graph a piecewise function. Now notice you've got 2 constant functions here, one at y equaling 3, which is right here, and one at y equaling 0, which is right here. Now, if we look at negative 3, it's only when x is less than or equal to negative 2. So here's x equaling negative 2. That means everything less than that, but I have to be at negative 3. So because I have an equals, I need a solid dot, and I'm going to choose everything left of it. And go ahead and do our 0, y equaling 0 for all values that are greater than 2. So here's y equaling 0. Here's x equaling 2, so I need everything that's bigger than 2 at y equaling 0. Again, those constant functions are those that go side to side. Okay? All right. And our last in-between piece is this line, x minus 1. Notice that is bouncing between negative 2, x, and 2. Okay? Now, if you want to, you can do a t-chart if you want. And the y value comes from taking x minus 1. So I'm going to do these numbers. Now, this one technically is not equal, but what would it be if I was up to negative 2? We would just symbolize an open circle there. So I'm going to choose negative 2, negative 1, 0, 1, and 2, just as my whole numbers. So if I plug negative 2 in my function and subtract 1, I get negative 3. If I put negative 1 in my function and subtract 1, I get negative 2. If If I put 0 into my function and subtract 1, I get negative 1. 1 in my function minus 1 is 0. And 2 into my function minus 1 gives me a 1. So if I plot those points, remember this first one was my open circle one. At -2, -3, well, that not always does this happen, but it actually overlaps the previous part. So we would not necessarily need to have an open circle there. So that's already covered. -1, -2, 0, -1, 1, 0, and 2, 1. And I did a solid dot there because there is the equals that allows for that. So if I want to connect those dots from -2 to +2, that completes the graph of my piecewise function. Again, you can graph them all individually, chop them up by the x values, and then get your graph. Okay? So we are done with section 1-2, and we will move on in 1-3 with some rates of change. Until next time.